All right, in this video, we're going to, I realized my diagram goes down below the window. Oh, whatever. We're going to tackle the area bounded by a polar graph, which is the last topic of the year. Before we get into the area bounded by the polar, let's look at this area bounded by just rectangular functions, right? If we have like the area of a region and we're trying to find what it is, really what we do is we kind of get, okay, Riemann sums, we're going to get all these rectangles. Each one of those rectangles has a height. And now if we're just integrating and we're getting the area bounded by one function, well, then the height is just that function, right? We can find this area bounded by the red by just integrating the red function. Or I could find the area bounded by the green by just having the height be the green function. Or if we have the region between two things, okay, the height is just the distance between those two things, right? Top minus bottom, or right minus left for a dy integral. But I get the height of each rectangle, and then I have that little width. This is what's cut off at the bottom. We have the width of each rectangle. So I know the area of each one of those little rectangles, starting with that first one. We'll start with the height, the area of each little rectangle, right? It's just the height times the width. But I don't want just one rectangle. I want all of them, starting with that first one, then this one, right? Then all of those rectangles, starting with that first one on the left, all the way to that last one. So that's the formula for one rectangle, height times width. And then we know we'd want to add all of them together, but I wouldn't want to just have n equals 10 or n equals 20 or 100 many rectangles. We would want infinitely many of those rectangles. And we know, hey, having a summation of infinitely many things, well, that's what an integration does for us, right? It compiles them all. So we have these vertical rectangles, and we're compiling them all. That's how we do the area rectangularly. What's going to be different is that now for polar, we don't really build things vertically because we're not really concerned about x's and y's. Really, everything with polar is more circular. So let's kind of talk about this. Right? How do we end up getting this area, a polar graph? Well, it goes back to some geometry. If I have, let's say, the area of a sector, right? We'll call that angle theta. We know the full way around the circle, that full way would be 360 degrees, but since we hate degrees, we know it's going to be 2 pi radians. And I could think about, hey, that area of that sector, it's just a certain percentage of the total, right? Like if this was 60 degrees, then all the way around would be 360, right? It'd be 1 out of 6, because 60 out of 360 is 1/6. Or if it was, I guess instead of doing 60 degrees, I should talk about pi over 6 radians. But that arc length, by the way, that's also the same. Like the arc length is just a percentage of the circumference. What percentage? Well, you take your angle out of the total, which is either 360 for radians, 360 for degrees, or 2 pi for radians. And we do the same thing for arc length. The area of that sector is just a certain percentage of pi r squared. It's just a certain percentage of that whole circle's area. And what percentage it was is it's just our angle out of the total. So our angle out of 2 pi for radians. And so this is our sector, area of a sector formula, which you should have seen in pre-cal. The pi's end up canceling, and then you end up having 1/2 r squared. So that's the area of a sector. And really what we're doing is we're going to be taking, hey, we want the area of that first sector, then we'd want the area of that next sector, and then the area of that third sector. Really, right, instead of breaking them down, and instead of having these Riemann sum rectangles from the left to the right, or from the bottom to the top, really we end up having these sectors from that kind of lowest angle, and then we're going to rotate, and then we'd end up having that last sector. So instead of accumulating the area of rectangles, we're going to accumulate the areas of a sector. And of course, as I have more and more and more, my estimation gets better and better and better. And then really, I'm going to want infinitely many of these little sectors. But instead of having the area of a rectangle, which is just height times width, here we're going to end up having that area of a sector, which is 1/2 r squared theta. Okay, so let's go kind of look through this. I'm not going to spend too much more time on it, but this page kind of just walks us through, similarly to what we did with Riemann sums, the different notation for what builds up to that area formula, right? Integrating to compile them all together. And what this is going to culminate, right, is we're just adding together infinitely many areas of infinitely many sectors, starting with that first one at that initial angle, and then rotating to this final one, right? We have this change in theta, and we're just accumulating all those areas of all of those sectors. And we know the area of a sector is 1/2 r squared theta. So that's what we're going to end up integrating. If we're going to look at this formula, it's really pretty simple. We're just integrating 1/2 r squared theta. But we have that little small change in theta, right? Those little angles, right? We have that here, right? This little change, that's my d theta or delta theta. And then as we have infinitely many of those little sectors, that delta theta gets really small. Just like how the width of those rectangles for Riemann sums gets really, really, really small. And we say instead of the change over an interval, dx, or delta x, we change it to dx, instantaneous change. We're going to do the same thing, right? That kind of width of that little slice or that wedge of my sector, that's eventually going to get really, really, really small. There you go, 1/2 r squared theta. And when we integrate them all, it's going to be 1/2 r squared d theta. And we're going to integrate to compile them all from that initial theta all the way to that final angle theta. So it's actually a pretty easy formula. Usually most of the trouble is figuring out what angles you're going to want. Sometimes that's simple, sometimes it's not as simple. But the formula for the polar area is actually really easy. 1/2 r squared d theta. Then we're going to integrate it over that kind of range that our angle theta can fluctuate through. Okay, so we're just going to try to get through all these different examples with polar area. I don't know how many I'm going to get through in this video. There's like a good amount. There's like 5 or 6 pages. Actually, there's 4 pages of notes. So maybe I can get like halfway through in this video, but I may just have to stop. But if I don't finish them all in this video, which I'm probably not going to, I'll just make a second video. But let's go for it. And remember, that formula was really not super difficult. 1/2 r squared d theta, and then from the lower angle up to the bigger angle. That's my area for polar. Here we go, first one. We got sketch the region, sketch the graph of r equals 2 plus 2 sine theta, and then find the area. So you got to know what that graph is going to look like. That's a limacon, but since the a value and the b value match, it's actually not just a limacon. That's a special type of limacon called a cardioid. So let's go for it. Remember, that tells me what to set. So r equals 2. That tells me, hey, I'm starting with the circle, but then I'm going to push inwards on it. I'm going to push it +2 in the y direction. So since I'm pushing vertically, those points stay the same. That point moves up 2, that one moves up 2, and it's actually going to end right at the pole. And so this graph is going to end up being a cardioid. And we could check it with the calculator too. Let's see, where's my calculator? There it is. Let's type it in. I already switched it to polar mode. So if we type this in, we have 2 plus 2 sine theta. I don't know what my window is, but there we go, right? So zoom square, so zoom 5. There we go. We've got this cardioid. There we go. I'm going to actually zoom it in. Whatever, I'm just going to leave it. Whatever. Don't care. We're going to leave it. And so we want to find the area inside that cardioid. So kind of really the whole point last time was to help us refresh ourselves over all those different graphs that we can see. So that way, when we're asked to find the area underneath it, we're not like completely floored. We're like, oh my gosh, what's going on? But we have to find the area bounded by this thing. We're going to start with the angle of 0. Then we're going to rotate around through all these angles. That's pi over 2. Then we're going to rotate all the way. That's pi. Then we go all the way, and we're actually going to rotate all the way from 0 all the way to 2 pi, right? 0 all the way to 2 pi. That's going to be our fluctuation for our angle theta. Now, all cardioids will end up being 0 to 2 pi. Now, the ones that have inner loops or the ones that are rose curves, those are going to be different. But all cardioids and dimpled limacons, that means they don't have the inner loop, all cardioids and dimpled limacons, all of them are going to end up being 0 to 2 pi. When I have an inner loop, that's not the case. When I have a rose curve, that's not going to be the case. We'll have to figure out what the theta values are. But all the cardioids and limacons are easy. 0 to 2 pi. Rotate all the way around the circle. There we go. Now let's go for it. Now we're pretty much just going to do it. Let's set it up. Here we go. Let's use orange. To find this area, we're going to have 1/2, 0 to 2 pi. And then we're going to take r. R is given to us. So it's 2 plus 2 sine theta. 1/2 r squared d theta. Like, okay, there we go. Got it set up. Now, a lot of the times the question is just going to be just set it up and then you're good, right? A lot of the times they won't really make you do it by hand. Or if they ask you for the area, you will probably have a calculator, and then you would probably be able to just use Math 9. If we don't have a calculator, then doing it by hand is possible, but it's not super enjoyable because they always end up being complex trig integrals. Going back to our techniques of integration, they're always going to end up being complex trig integrals because we have trig squared. And so, yeah, let's do this one by hand, but then pretty much otherwise, we're either just going to, if it's non-calculator, we're just going to set up the integral. We're not going to evaluate. Or if it actually does want us to evaluate, we'll use the calculator. But just for the sake of kind of seeing one example how it would be done, let's multiply this out and let's do it by hand. So we've got the 1/2, 0 to 2 pi. We're going to FOIL this out. 2 times 2 is 4. Then we're going to have 4 sine plus 4 sine, so it's going to be plus 8 sine theta, and then plus 4 sine squared theta. So there I just kind of FOILed everything out. And the 4 is easy to integrate. And the 8 sine theta is easy to integrate. But the sine squared, oof, I don't want to do that one. So remember, if I have sine squared, it's going to be 1/2 of 1, that's minus cosine of 2 theta, right? Whatever this angle was, it's going to double. When I use that power reducing identity and I go from sine squared and I reduce it to linear cosines, it's 1/2, 1 minus cosine 2 theta. If it would have been a cosine squared theta instead, right, it just would have been 1/2, 1 plus cosine 2 theta. But we had those power reducing identities, and usually one of them is going to come up. Since we have r squared, our r is going to have trig, that means you're pretty much always going to have one of those power reducing things to come up. Even power of sine and cosine, kind of annoying. But anyway, here we go. We got 1/2, 0 to 2 pi. We have the 4. We have plus 8 sine theta plus 4. And then that power reducing thing, we got 1/2, 1 minus cosine 2 theta. There we go. There we go. Let's just simplify it, and then we'll end up being able to integrate. Let's see. All this, right, 4 and 1/2, all that's just 2. And I could actually take this and distribute. So here we're going to have just 0 to 2 pi. 1/2 of 4 is 2. 1/2 of 8 is 4 sine theta, plus I had a 2, and then I'm going to do 1/2, so it's just going to end up being 1 minus the cosine 2 theta. And then I have the 2 and the 1, and I'm going to combine those. So the 2 and the 1, I'm going to combine them, and we're just going to have 3 plus 4 sine theta, and then, ooh, that one should have been a minus. I dropped my sign. It was a minus, right, because of this. So, like, doing all that was a little bit annoying, but we should be able to. We learned how to do those complex trig integrals. It's not going to make you do it on the AP exam. If area over a polar curve comes up, which it will probably, it will either be a non-calculator question in which all you will have to do is just set up the integral. They won't make you evaluate it. Or if you have to actually find the area, you will have a calculator. They're not going to make you do this by hand. Right, but if we wanted to, we could. This one would integrate. The integration of 3 is theta, or 3 theta. Then the integration of 4 sine would be negative 4. Come on, smartboard. That's not 4. Negative 4 cosine theta. The integration of a negative cosine would be a negative 1/2 sine 2 theta. So there's the integration. And then we could plug in 0, and we could plug in 2 pi. And then if I plugged in 2 pi, 3 times 2 pi would be 6 pi, right? We have the upper evaluation minus the lower evaluation, minus, let's see, 4 cosine of 2 pi. 2 pi is this angle. Cosine of that is 1, minus 1/2. 2 pi times 2 would be 4 pi. 4 pi is still going to land me right there, and the sine of that point is going to be 0. So there's the upper evaluation. And then minus, we have the lower evaluation, 3 times 0 is 0, minus 4. Cosine of 0 is 1, and then sine of 2 times 0 is 0, sine of 0 is 0, so that's also going to be minus 1/2. I don't know why I have that 1/2. It's definitely just a 1. Actually, no, the 1/2 came from the use of. That's why I have the 1/2. There we go. But sine of 0 is still 0. So look at all the stuff that cancels. That's going to be 0, that's going to be 0, that's going to be 0. And then here I've got that negative, which distributes. So that's going to end up being a plus 4. And then we have really this ends up canceling with that. And so what do we end up with? We end up with 6 pi. So the area of that region actually ended up with a pretty nice, pretty easy answer, 6 pi. Now, you had to do some work to get there. You had to multiply it out. Then we have one of those complex trig integrals where the power reducing identity came up. And then we had some work. Could we do it by hand? Yes, you should be able to. If you want to be any type of a STEM major, you probably need to be able to do those. But for the AP exam, they're not going to make you do it by hand. If it's non-calc, they will just have you set up the integral. Or if it's a calculator, you'll be able to math 9 it. By the way, let's just check it. Let's use the calculator and let's check it. Remember, math 9 with our GDC, that should hopefully be able to get this thing done. Let's see, switch it back. Let's get out of there, quit. Let's do math 9, and then I guess we need to put the 1/2 in first. So do 0.5, math 9, and then let's see, I have 0 to 2 pi, and then I had r squared, so I'm going to type in the r value, which was 2 plus 2 sine of theta, close the parenthesis for the theta, close the parenthesis for the r value, then the whole r value is squared. Bam, that looks good, and then here we go. Define the variable, and then there we go. We got 18.845, like Mr. Bell, we got 6 pi. What's going on? Well, 6 pi is that number. Okay, so we could do it by hand, and then we could get the exact value. It's going to be in terms of pi in all likelihood, or we could use the calculator. And the calculator is just going to give us the decimal. Right? The calculator, where do I want? I want that one. The calculator is not going to end up giving us, come on, the calculator is not going to give us this. It gives us that 18 point whatever number, but that's okay. Right? Most of the time, the questions are going to be non-calc, and so you'll just have to set up the integral and then you'll be done. Or if it's a calculator question, they'll probably just have the decimal answer. Or you could just always check 6 pi, see if it matches the decimal, which it does. We can do them by hand, but we're really not going to have to. Okay, let's move on to the next one. 1/2 r squared, that's what we integrate. 1/2 r squared. It's that coming from that area formula of a sector. All right, here we go. Let's do the next one. Here we've got 2 sine 3 theta. This one's going to end up being a rose curve. Now, my n value is 3. That means I'm going to have, not 6. If the n is odd, that means I'm going to have 3 petals. It's a sine graph, so it's going to have one on that bottom y-axis. And remember, all the petals are congruent and equally spaced. The length of the petal is going to be 2. There's going to be 3 of them. The first one's going to be down here. Then we're going to have one up here, and we're going to have one up here. Let's go look at the calculator just to make sure. I always like to watch the order in which it goes also. So I'm going to go type this sucker in. Let's get out of there. We've got 2 sine 3 theta. Close that. I'm going to go change my theta step. Let's change it. That's at 0.13. Let's try this. That may be too fast or maybe too slow. Let's try it. Yeah, that's a little. Okay, I'm gonna make it a little bit slower. Let's try 0.005. And I'm gonna actually go to my y equals, and I'm gonna change this. I didn't do it last time, which I should have. But I'm gonna change this so that we get the football. Oh no, come on. I want the football. There we go. All right, here we go. Let's graph it. Oh, I made it too slow. Now it's going really slow. I made the theta step too small, so it's going really slow. I regret everything. Okay. Too slow. Quit out. Come on. Oh, it doesn't even let me kill it. Okay, well, we're just gonna have to suffer through this, and it's like slowly. Did I freeze it? Oh no, there it goes. Okay, let's go change this. The 0.005 was too slow. Let's go back and let's just make it let's make it faster. How about let's just do the 0.01 then. Okay, there we go. Maybe I added an extra 0. So here it goes, right? It starts off at the pole, then it goes around. It actually creates that pedal in the quadrant 1 first, and it comes around. It does the left side of the bottom pedal, loops back around, and then it's going to go do that third pedal. And then actually, like watch what happens. The football is going to go around again, right? Because here, I'll show you in a minute. But the theta for this calculator is 0 to 2 pi. But since that argument was a 3 theta, it's actually going to go around multiple times. Let's see if it goes around. Now here it's completing that second circuit, and then, ooh, there we go. So it actually went around twice. Right? Did you guys catch it? I hope so, because I don't want to watch it do it again. Here, if we look, actually, I want to go back to that. Oh gosh, come on, Mr. Bell, get it together. Here my theta min was 0, my theta max was 2 pi, right? And so over that interval from 0 to 2 pi, right, when I graphed it from 0 to 2 pi, catch the order, this is what it looked like. It started here, then it did this, then it did that, and then not only did it complete the whole graph, it actually went around twice, right? So 0 to 2 pi, it went around twice. It was like bam, 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 right? And we don't need it to go around twice. In fact, we don't even need the whole graph, because what this question wants is to find the area of just one pedal. And that first pedal that it graphed, right, that thing started here, and then it did this. That was like the first thing that it did. That's why sometimes I like to turn the football on. So I'm not going to need 0 to 2 pi. In fact, I don't even need 0 to pi, because 0 to pi, right, what this does is that went around 0 to 2 pi went around twice. If I just did 0 to pi, you could change it, right? You could go to your calculator. I always like this. You could go to your calculator and you could just change the theta max, and you can just make sure that you're only going to be graphing the part that you want. 0 to pi would actually complete the whole figure. It would be like this. 0 to pi would just the whole thing, but you don't need the whole thing. You just want this. So we only need the theta values for really that initial time is going to be from 0. But then I need to figure out what that angle is going to be. And that angle is when it gets back to the pole, right? It started at the pole, and then it looped around. And when it gets back to the pole, when r is 0, that's when it's going to stop. Okay, so I don't need 0 to 2 pi, because that actually would get 6 pedals. If you did 0 to 2 pi and then divided everything by 6, that will work. Or if I did 0 to pi and then I divided by 3, that would work, because all the pedals are congruent. You just kind of have to pay attention, like how many times is it going to go around, how many pedals are there, and if you get kind of something that you don't want, like I only want 1 pedal, so I don't want the whole thing twice, I don't want 6 pedals. But if you did 0 to 2 pi, divide it by 6, that'll work. Or if I did 0 to pi, then I could divide it by 3, that will work. But really, we want to find the theta values that's only going to graph 1 pedal. And how we do that is we just set r is equal to 0. So here we go, 2 sine 3 theta, we want that to be 0. So that means, right, divide by 2, it doesn't matter. Sine of 3 theta is equal to 0. That means, right, here's a trig equation. There's infinitely many values that this is going to work for. Right? So if I'm thinking about sine of some angle being 0, there are 2 points on the unit circle where the y value is 0. There's this one and there's that one. Negative pi would work. There's infinitely many solutions, but negative pi would be 1. 0 would work. Pi would be 1. 2 pi would be 1. 3 pi, right? Basically all your whole number integer values of pi, both positives and negatives, those are going to work. And then we would get it not from 3 theta, we're going to want just theta. So again, we're going to have negative pi over 3, 0, pi over 3, 2 pi over 3, 3 pi over 3, that's just 1, so on and so forth. And when we've solved this, right, that's a trig equation, which you should have learned how to do in pre-cal. That's kind of one of the harder ones in pre-cal, but we should know how to do it with that weirder argument. This right here is all of the time values where my graph is at the pole. Remember, it starts at the pole, then it loops around, right? And when it finishes that first loop, we're at pi over 3. Then it looped around again, then it was at 2/3. Then it looped around, it was at pi. Then remember, for the 0 to 2 pi, it actually went around that second time. But I don't need it all that time. I don't need a -1. I don't need to go around twice. So really, all I want for that first pedal is just the first time when it's at the pole, which is at 0, and then to that next time it's at the pole, which is at pi over 3. So there we go, right? That would be the integral that would represent just one petal. Again, we have area equals 1/2, then it's going to be r squared, so we just plug that in, 2 sine 3 theta squared. But if I only wanted one petal, I could do 0 to pi over 3. And that would be the integral that you would want. Again, we can math 9 it to then go get the answer, but we usually don't have to. There are other things you could do, right? Like if I did that integral from 0 to 2 pi, I have 2 sine 3 theta squared. Don't forget, every time you do the formula, you need the 1/2. That's from the arc length. But if I did 0 to 2 pi, we have this, right? We actually have 6 petals. So then you could divide it by 6. So if I put 1/12 of that integral, that would work. 1/12 of the integral from 0 to 2 pi, that would work. Or if I did 0 to pi, that's going to end up getting you 3 petals. So if I did 0 to pi, remember this right here, this right here, that would be 3 petals. That's the full rose curve, that's 3 petals, but I don't want 3 petals. I would want just one of them. So then I could divide it by 3. And so 1/6 of the integral from 0 to pi, like that would work. If you were to math mine this, or if you were to math mine this, or this, they should all give you the same thing. Okay, but if we're going to set it up, we're going to set up the easiest, hopefully most simplified one, which is, hey, what are the actual values? That thing started at theta equals 0. It started at the pole, and then I just need to figure out that first time it gets back to the pole. So you just set r equals to 0, and then you solve it. There are other equivalent ones that you could do, but yeah, there we have it, right? That's kind of the best way to go about doing it. Find the theta values that you want, and then you could think about symmetry, but I mean, a lot of the times that's kind of just harder. Okay, let's clear some of this stuff off. Let's see, I need to get that. Okay, let's get rid of all this, and then here we go. Let's look at the next one. We'll probably just do this video, we'll do this example, and then I'll probably be out of time because I need to teach my next class, and then I'll make the next video to hopefully finish some of the rest of these polar areas. Here we go, last one. Sketch and set up an integral expression to find the area. Again, it's just one petal of 4 cosine 2 theta. I don't even remember. Did we look at that rose curve? Did we do it? Oh, we did. That's right. And we haven't turned it. Let's go do this new one. So we've got, it was 4 cosine 2 theta. 4 cosine 2 theta. Now, before we actually look at it, let's think about and try to plan what that thing's going to look like. It's got a 2 theta, right? My n is 2, so that means I'm going to have 4 petals. Cosine means one of them is going to be on the right side of the x-axis, and then of course the L is going to be 4. So I'm thinking this one's going to go out to 4, then it's going to have another one, and it's going to have another one. Oops, it should go out to 4, and then it's going to go down to 4. Come on. Remember, all the petals are equally spaced and congruent. If there's 4 of them, that means they're 90 degrees apart, right? So one of them's on the positive x-axis, and then the other ones are going to be equally spaced. So therefore, they're all going to be on the axes. Let's go look at it. Again, you could change your theta step, but what you want to pay attention to is where does the graph start, and then what's kind of the order in which it graphs. Notice it started on the right side, then it came around to the pole, then it loops. Now it's the first one that's actually complete is actually that bottom petal, and then it's going around and doing the left petal, then it's going to loop up and do the top petal. It's kind of nice that it's slow because we can watch it, but sometimes I just wish I could hit the fast forward button a little bit. You can always change how fast it goes by changing the theta step. And there it goes. It finally is going to come back around and finish that first petal. And look, it's not going around again. So 0 to 2 pi actually created that whole graph, right? So always putting that little football on the graph is pretty nice. 0 to 2 pi gave us that whole graph. Come on, smartboard, goodness gracious. 0 to 2 pi gave us the 4 petals. So if I were to just do like 1/2 r squared d theta, right? If I were to do 0 to 2 pi, I could just divide it by 4 and end up having a 1/8 out in front. Like, that's not wrong, but that's probably not what one of the multiple choice options would be. Okay, so here is kind of what we would do. Again, we would set the r equal to 0, and we're going to solve it. So we got 4 cosine 2 theta is equal to 0, divide by 4, so I've got 2 theta, that's going to be equal to, let's figure out cosine 0, that's this point on the unit circle and that point. So we've got negative pi over 2, we've got pi over 2, we've got 3 pi, it's all the half of pi, right? 5 pi over 2. That list goes infinitely long. There's infinitely many, right? Infinitely many coterminal angles that will either land us here or there, which are the two spots where the cosine is 0. But then we don't want the solutions for 2 theta, we want the solutions for theta. So let's divide everything by 2. So we've got negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4, dot, 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 right? That list would just keep going. Now, remember the order in which this thing graphed. Right, let me do it in green. It actually started here, and then it did this. Notice, at theta equals 0, it was not at the pole. 0 is not in this list of solutions, right? This is telling me all the times it's at the pole. 0 is not one of them. But that first time it gets to the pole, did you catch it? It's pi over 4. And then really, if I were to graph this, right, if I were to do pi over 4 to 3 pi over 4, which pedal is it going to get you? Well, this would actually give us this pedal. And then if we were to do 5 pi over 4, wait, it started over there, there's the 1/4, then to 3/4, then it did this one. So that would actually be the 5/4 to the 7/4, and then it would just keep going, right? Because then it did this, and then it actually finally came back around and completed that first pedal. Does it matter which two values we use? Well, no, not really. It doesn't matter. And really, there's lots of things that you could do. I could even just do this. If I used those two, really negative pi over 4, let's back it up. If I were to just use these two, let's look at this. Let's look at the calculator. Let's see. Let's change it. So instead of the theta min, let's do negative pi over 4, and then let's just do, I don't want it to do the whole thing again. Let's just do pi over 4. And let's see, the theta step's probably fine. Here we go. Ooh, so if I changed it, so now it's negative pi over 4, I actually kind of reset it. And then now this is actually going to be doing that pedal on the right. And it had better only do that one pedal. Yep, and then it stopped, nothing else. So when I actually went back and I got this, that's kind of going back and getting this yellow slice, but from the previous rotation around. But you could do lots of things. I could do the integral from this to this. Really, it doesn't matter because of symmetry. Really, even if I just did 0 to pi over 4, 0 to pi over 4 would only be half of a pedal. But if I did 0 to pi over 4, then I could just double it, right? So here, if I did 0 to pi over 4 of r squared d theta, right, this is 1/2 of the pedal. Right, because it starts over here at 0, then it traces that, and that would be the interval 0 to pi over 4. But then if you just doubled it, that integral would work. 1/2 and the 2 would cancel, right? Because of symmetry, if you only do half of the pedal, multiply it by 2, and then that's actually kind of nice because you don't have that 1/2 in the front. So that one would work. Or if you really wanted one full pedal, you would kind of want to go back. You could use pi over 4 to 3 pi over 4, or really it doesn't matter. You could use any two of these numbers because it doesn't even have to be one whole pedal. Half of one pedal, right? If I did 0 to 3 pi over 4, then it would be that part, and then it would be that part. But I mean, that would still form one whole pedal. But typically, probably what I would do is 1/2. That was terrible, smartboard. That was atrocious. I would do 1/2, then I would just do this one to this one. That was one pedal, right? Negative pi over 4 to pi over 4. We just trace that, and then we plug it in, right? We have 4 cosine 2 theta d theta. And so that kind of like changes things, right? I mean, there's lots of different ways that you can write this and be correct, especially if you use symmetry. If I get too many pedals, if I did 0 to 2 pi, that's actually tracing the whole thing. That's 4 pedals. If I did 0 to 2 pi, then I could just divide it by 4, right? That's kind of what we talked about over here. Or if I only did half of a pedal, which would be 0 to pi over 4, well, then I could double it. But if you want one complete pedal, you just got to like set that equation equal to 0, figure out which two theta values are going to work. Honestly, you can kind of pick any one, but if you just want to shade one complete petal, the negative pi over 4 to the pi over 4, that did get us that whole petal. And again, graphing it in the calculator is like a really nice thing. Just check it, right? Let's see. It's window, not mode. You can always just change your theta min to your theta max, and changing these two things and producing the graph and looking at it should be a good way to check and make sure that you're actually generating the region that you want. And you're not getting extra things. You're not counting things twice. Sometimes it's hard to see that something's going around twice. So you may want to turn on that football to see that, hey, that thing actually went around twice. Without the football, you're just kind of messing with the calculator, like, why won't it let me change the screen? Because it's still going around. It's just going around that second time. Yeah, turning on the football is nice. Paying attention to the order in which it graphs. Like, where does it start? What's the pattern? What's the path that it traces throughout that region? How many petals does it form? How many do I really want? Using symmetry, there's lots of different ways you could write these answers. But just use the calculator. Calculator is your best friend. Lots of different ways you could write it. Just conceptually make sure you're going to end up with something at the end that is equivalent to what you want. If you want one petal, you don't want 0 to 2 pi. If you do the whole thing, you're probably going to have to divide it by something. Or if you only get half of a petal, double it. In fact, that kind of looks nice, right? Because then I could have those cancel, and then I could have, let's do it over here. I need a different color, right? I'm just going to rewrite this one over here. It's just 0 to pi over 4. Then it was r squared d theta. And then my r value was 4 cosine 2 theta. Like, that's fine. And honestly, that one probably looks, these two are equivalent. But that one in the top left, that green one, it probably looks nicer because you got a 0, right? Having a 0 is nicer than having the negative number. And then not having the 1/2 is probably nicer than having it. So this is probably the easiest one. Like, if you actually had to work it out and do it, that's probably the one you would want to work with. But there's other ones you could set up and would be equally correct as doing. All right, there are multiple more examples. There's kind of 2 more on the next page, and then there's 2 kind of free response type questions. I will make at least 1 more video. It's possible I may have to make 2 more videos. That was obnoxious. I will make some more videos going through the rest of these polar area ones. But as you just heard with the bell, I got to stop right now because I got to teach my next period class. But yeah, hopefully it makes sense, right? 1/2 r squared, that's what you integrate. It's coming from that area of a sector formula from pre-calculus. 1/2 r squared, that's it.